All right, B4. So this is the lithium problem with particle in a box. Right. So we can take the particle in a box theory and approach, and we can apply it to actual like chemical concepts and get an understanding of it. So we in class we've talked about atomic orbitals and everything. And so what happens when atoms bond together is that those orbitals start to overlap and then they start forming molecular orbitals. And so I think next week is when you guys will go over those. Um, and so what happens is that they all combine together, and then all the different electrons, right, they get shared between all the atoms, and then um, they form new wave functions that are combinations of all of the wave functions of all the atoms that are participating in those cases. And so we can still use the particle in a box approach if we're thinking like, okay, right, we have a lithium, a chain of lithium atoms, like so if it was just like metallic lithium, right, and we're saying it's 4 lithium atoms long, and we can be like, okay, well, how does do the different electron levels actually then relate to each other? And it's exactly the same concept that we would have applied to a regular old particle in a box that did not include lithium atoms. Right, we have the length of the box, which is just simply the length of that chain of lithium atoms. Right, and the electrons are still going to be shared across all 4 of those atoms, right? They're not localized specifically on a single atom anymore, or even between 2 individual atoms, even though that's what a Lewis structure will tell you. Right, those electrons are actually distributed across all the atoms in those different cases. And we can use the particle in a box to kind of get an idea of a very simplified approach of what the molecular orbital would look like within that chain where all of those were together. And so the first part is, right, predict the shapes of the bonding wave function at the different energy levels. So it's the exact same thing that we would do with a regular particle in a box, right? We have our right, we have our n equals 1, our n equals 2, n equals 3, n equals 4, n equals 5, right? And so if our boundary conditions, right, are the length of the chain, right, we would expect to have one wave that is just simply looks like that goes all the way through, right? We would expect one wave, the n equals 2, then to have a node that's the halfway point, right? And so then that would probably be between the n equals 2 and the n equals, or not the n equals 2, sorry, the second lithium and the third lithium in these cases, right? So you'd have one phase that goes up, and then you'd have one phase that goes down, right? You go n equals 3, you start cutting it into thirds overall, right? So you get something, where it's like, here and here, something like that, right? And you get, a wave function that looks like something like this, right? You do n equals 4. Again, right, all we're doing is just simply the same thing that we've done for a regular old 1D particle in a box, right? It's the same exact approach. There's no difference. Right? So that's what, from a 1D particle in a box perspective, that's how we can approach it in this case. And so, if we locate all the nodes, thinking about what is the significance of these nodes, right? The definition of the node hasn't changed from any other point, right? The node is a point where you would have 0 probability of finding an electron in these cases, right? So you would not expect to find an electron at any of those nodes. And so, the significance is that between some, when you move to higher n levels, there's going to be then regions in between atoms where you're not going to expect any electron density for those orbitals. Right, so in the n equals 1 level, you don't have to worry about that. But when you go to the n equals 2, right, there's going to be a region between the lithium 2 and the lithium 4 atom that is going to have 0 electron density, or not necessarily 0, 0 electron density, right? Because the probability is going to be equal to 0, right? You're going to have that between those two, right? You go to the n equals 3, right? You're going to have one that's kind of cutting up the lithium 1 and lithium 2 and lithium 3 and lithium 4, right, and so forth, right? Those are all going to be points where you're going to be cutting those up. And so when you start talking about and thinking about molecular orbitals, next week or the week after or something, that's when you start learning about bonding and anti-bonding combinations, right? And so that's what's happening, is that you start getting combinations of both bonding interactions between 2 atoms, but also anti-bonding. And all anti-bonding just simply means is that they're that you have a node in between 2 atoms. When we're talking about it from a molecular orbital perspective. And so, that's all, you're really looking at here, right? Is the regions where that happens. So there is a strong resemblance between particle in a box. Exactly. Yeah. So you can apply, right, that very simple particle in a box, wave function approach, right? That theory, even though it seems like a very abstract thing, you can start applying that to chemical systems. Now, it doesn't like match one to one in terms of like, oh, right, the energies and stuff like that. And like, you have to think about the fact that, I mean, it's the same thing with like, applying the particle in a box to like atomic orbitals, right? A lot of the stuff is still the same. The only difference is that in atomic orbitals, right, as you move further and further away from the nucleus, right, the amplitude decreases until eventually you get to zero for, the probability and everything. Whereas, in a particle in a box, right, it's just a perfect sine function that there's no difference anywhere. Right, and you're saying like, oh, it's in this like specific container, whereas, in the case of an atom or a molecular orbital, right, there's technically infinite space that it could travel, even though it becomes, infinitely improbable for an electron to exist, that far out, in those cases. So, but you can still apply, right, like that same idea to getting an understanding of what's happening. And that's what, if you go to, I'm going to jump ahead to part D, right? So these are calculated molecular orbitals, right? So these are simply showing, the actual, bonding orbitals that exist. And, they kind of match pretty closely with what we got for the particle in a box approach, right? So I have, on the right side here, my, the drawing of all of the different, 1D particle in a box for the lithium chain, that I had expected, just using, again, what we know about 1D particle in a box and how to draw the different wave functions and where we would expect for nodes to be just based off of the 1D particle in a box. And then here on the right, or sorry, on the left, right, I have, the calculated molecular orbitals. And so we can see, that there's one case where you have just simply, a single phase across all four atoms, right? That's this guy right here. Right. And so we would expect that to be, the n equals 1 level, in terms of relationship, right? We can see that we have one case where we have a single node in between the lithium 2 and the lithium 3 atoms, right? Where we're seeing a difference in phasing between, the blue and the red. So that's telling us, right, that this is going to be the n equals 2, right? Because that matches what we have right here in this case. We go then to the next one, right, where we're expecting, some kind of change in phasing, between, 1 and 3, and then 2 and, or sorry, and 3 and 4, with, one phase in between 2 and 3, right? We can see that right here, right? So this would be the n equals 3 that we would expect, because again, right, you have, roughly a node that exists right there. We're like, look at this guy right here, we're expecting, the n equals 4 right here, right? We expect one node in between 2 and 3, and then we expect another node between 1 and 4, right? And so this one kind of matches pretty closely. Still looks kind of funky and everything like that, right? It's not like a perfect positioning, right? But it kind of matches with, again, our extremely simple model, right? Where if you wanted to, you could always hypothetically plot, all of these different things in your calculator, for the different wave functions and stuff for these distances, and you can, relate that to like an actual, like, using the supercomputer on campus to calculate those molecular orbitals and be like, okay, right, it matches, for the different level of theory pretty well, right? And so this is, the n equals 4 right here, right? And then we go here, right? And so now, right, we're expecting nodes to essentially sit, right, because there's 4 nodes. We're going to expect those nodes to kind of sit on each one of the lithium atoms for the n equals 5 case, right? And we can see that here, right? We have a node on this lithium, this lithium, this lithium, this lithium, right? So all of those match in those cases, right? And so again, is it a perfect relationship? No. Is it pretty close for what we're expecting? Then so no. So for the angular radial nodes, that gets thrown out the window, that concept, for molecular orbitals. Right, you don't really think about angular nodes and radial nodes in those cases, because what you start thinking about is what's referred to as like a sigma bonding orbital, or a sigma anti-bonding orbital, or a pi bonding orbital and a pi anti-bonding orbital, or a delta bonding orbital, or a delta anti-bonding orbital, right? So the way that you think about and approach nodes for molecular orbitals, which is what we're looking at in this specific case right here, is different from how you approach it and think about it for atomic orbitals in those cases. So once you guys get to molecular orbitals, right, that's when you guys will go over all of that stuff. The angular and radial stuff, right, dictates whether something is, a p orbital or a d orbital or an s orbital, or is it at n equals 2 or n equals 3, n equals 4, and so forth. When you start getting to the higher level ones, right, that then kind of like goes or sorry, to the molecular orbitals, right, things kind of like switch of what your perspective is and what you're focusing on. And so once we get to those, right, we'll talk about those. Oh wow, it's already 10:30. All right, and then part C, right? I think that's the only part I skipped over. Yeah. So part C then is just simply calculating the energy. And so, in this case, it's very similar to what we've done in the past, right? We have our energy equation here. And so the question, right, is asking, what's the wavelength of light required to move from the n equals 1 energy level to the n equals 2? So the first step is to, excuse me, is to calculate what the energies are for the two of them, right? So E of 1 is going to be equal to, h squared over 8ml squared times n squared, right? And so in this case, m, right, we're talking about an electron, so that is what, 9.11 times 10 to the negative 31 kilograms. L is equal to 9.036 angstroms, right? And so an angstrom is 1 times 10 to the negative 10 meters. So that just simply becomes 9.036 times 10 to the negative 10 meters. Right? And then H is just simply 6.626 times 10 to the negative 34 joule seconds, right? So we plug all of that stuff in here, right? So E1 is equal to 6.626 times 10 to the negative 34 joule seconds squared over 8 times 9.11 times 10 to the negative 31 kilograms times length is 9.036 times 10 to the negative 10 meters squared times 1 squared, right? Because we're at the E equals 1 level. So plugging all of that in, so we have 6.626 times 10 to the negative 34 squared divided by 8 times 9.11 times 10 to the negative 31 times 9.036 times 10 to the negative 10, and then that is squared. And then multiply that by 1 squared, which is 1. What you get is 7.38 times 10 to the negative 20 joules, right? And then we can apply that same thing to E2. Now we know, right, that this whole thing is equal to this whole part right here. So all we have to do is just simply multiply that value that we just got. We can just take the E1 level and then multiply that by 2 squared. So what we get in this case is 2.95 times 10 to the negative 19 joules, right? And so now what we need is the difference in the energy levels. So delta E in this case is E2 minus E1, which is 29.5 minus 7.38 times 10 to the negative 20 joules, right? And so all I did was just simply shorthand that out, right? Because instead of writing out two different scales in those cases, so you can kind of, do some of that math in your head if you wanted to. But 29.5 minus 7.38 comes out to being 22 12 times 10 to the negative 20 joules, right? So we know we have that energy, so now we need to convert that into wavelength, and so that equation, right, is equal to hc over lambda. And so if we want to get lambda, right, what we have then is H, which is 6.626 times 10 to the negative 34 joule seconds, times speed of light, which is 2.9979 times 10 to the 8th meters per second, over energy, which is 22.12 times 10 to the negative 20 joules. And so then the wavelength comes out to being 6.626 times 10 to the negative 34 times 2.9979 times 10 to the 8th divided by 22.12 times 10 to the negative 20 comes out to being 8.98 times 10 to the negative 7 meters, which is the same as, right, times 1 times 10 to the 9th, 898 nanometers, which is the lithium problem. Yeah, is what I got here, right? So 897 nanometers, what I hear. Would it be all right to multiply 7.38 times 10 to the negative 20? Yeah, that should work as well. Right. I mean, you should get the, I mean, that, right. I mean, that should come out to the exact same result. Cause if you, right, if you were to just simply like do that whole thing, that works as well. I just wanted to go like step by step, right. Just to show where we're at. You know, if you do have, you know, shortcuts that you're comfortable with doing, right, that's perfectly fine and everything. So, yeah, that works. I mean, that you should get the exact same answer. There shouldn't be a difference, in those cases. Cool. All right, so let's see.